Computational limits represent the primary barrier to building artificial intelligence with a persistent memory. Most language agents operate on a react loop. The model alternates between reasoning about a problem and taking an action to solve it, like querying an external tool. Every time the agent retrieves a memory, it must re-ingest the entire conversation history to process the new data. Running 0 tool calls establishes baseline inference cost. Initiating a single memory retrieval doubles that input cost. 2 sequential calls triple it. The model cannot reply until it processes those massive context window resends, introducing a severe latency penalty. Because of this geometric expansion of cost and time, relying exclusively on on-demand data retrieval makes persistent AI companions economically impossible at scale. The engineering solution to this bottleneck requires bifurcating memory operations into 2 strictly defined data streams. The first stream is a highly compressed mental model. We preload this directly into the system prompt at the start of every single turn, ensuring baseline awareness at 0 marginal retrieval cost. The second stream is a massive, externalized archive. The agent can only access this data via targeted tool calls when it specifically requires deeper context. We employ a rigidly targeted bifurcation instead of the standard RAG pipeline, which often dumps unstructured chat history directly into a vector database. This diagram outlines the framework governing the split, a 4-tier compression stack. It organizes data starting from raw episodic logs at layer 0, compressing upward to synthesized awareness at layer 3. Building artificial memory is an exercise in ruthless data compression and token governance. We design our data pipelines to match the cognitive outcomes humans achieve: continuity, pattern recognition, and selective recall, rather than attempting a literal simulation of biological brain mechanisms. That process begins at layer 0, the foundational tier of the compression stack. Layer 0 consists entirely of raw, immutable episodic history. It is the verbatim log of every message exchanged. Searching this raw data is computationally massive. Transmitting thousands of uncompressed conversational turns requires extensive token expenditure. Therefore, we enforce a strict limitation on L0 retrieval. The agent only accesses this layer to answer precise temporal queries that demand exact historical quotes. Raw conversation logs provide necessary ground truth, but their sheer volume makes them ineffective as an active, continuous context for behavioral prompting. To create active context, we move to layer 1. Here, we extract structured, queryable knowledge from the raw episodic logs. We built a graph relational model natively within Postgres. Layer 1 converts extracted facts into distinct entities and relationships, pairing them with PG vector embeddings for precise semantic searchability. This graph structure enables multi-hop relational queries, preventing shadow filtering errors where valid context is retrieved but ignored. We then attach an explicit emotional memory weight directly as metadata onto these graph edges. Facts extracted during highly intimate or vulnerable conversations receive a permanent quantitative importance boost up to 15% over mundane details. Layering relationship data with emotional geometry forces the AI to prioritize information that holds functional significance to the user, bypassing simple keyword matches. Above the facts lies layer 2, the analytical tier. Here, the system infers abstract behavioral patterns from the structured graph. Secondary language models analyze the accumulated L1 facts to deduce user insights, such as communication preferences, and define proactive procedural goals for the agent to pursue. But layers 1 and 2 share a structural vulnerability. Without a mechanism to prune the database, it expands infinitely, which rapidly degrades both retrieval accuracy and speed. We solve this using asynchronous background workers. While the user is offline, the system performs sleep consolidation routines. These workers execute specific maintenance operations. They extract new graph nodes, summarize long bursts of chat, and enforce memory decay. This chart tracks our decay mechanism. Using tiered algorithms, we prune low-importance data over time. You can see standard data points fading to 0, while emotionally boosted facts remain stable and accessible. A functional long-term memory architecture requires an active, automated mechanism for forgetting to maintain system efficiency. The apex of the cognitive compression stack is layer 3. We call this the companion journal. It is a highly curated, holistic summary of the user's identity and the current state of their relationship with the AI. We apply strict token governance here, mathematically bounding this layer to approximately 750 tokens. Background workers compile this dense text block nightly. It is then slotted directly into the system prompt at the beginning of every single turn. This provides the agent with instantaneous context, answering the question, "Who is this person to me?" Layer 3 entirely circumvents the React loop token multiplier. It delivers empathy and critical context at zero marginal retrieval cost. To trace this architecture in motion, consider a user inputting, "I'm stressed about my presentation." Step 1 is instantaneous. The preloaded L3 journal informs the agent of the user's baseline anxieties and communication preferences before any tools are called. Next, the agent executes a targeted tool call. It queries the L1 graph specifically to retrieve the node labeled Board Presentation. The agent merges the empathetic baseline from L3 with the factual data from L1. The result is a highly contextualized, accurate reply. Post-interaction, the new user message drops securely into the massive L0 raw episodic logs. Later, during the offline phase, background workers process that L0 log. They update the L1 graph confidences and resynthesize an updated L3 journal for the next day. Orchestrating this multi-tiered flow creates the outward reality of persistent artificial cognition. Standard industry practices rely almost entirely on single-tier retrieval. Simply increasing the storage capacity of a vector database fails to produce relationship-aware, computationally efficient AI. It creates an unmanageable archive. The economic efficiency of this architecture stems from separating compute operations into two categories: expensive, targeted queries, and cheap, generalized preloads. Furthermore, long-term system stability is impossible without an active forgetting curve and offline consolidation workers to manage database decay. The engineering of agentic memory relies on rigorous tiered compression, continuous background consolidation, and strict token cost governance.